Hi everybody, welcome to this video on calculating volume by rotation using the disk method. This is also known as calculating the volume of solids of revolution. The most common application of the method of slicing is calculating the volume of solids of revolution. So we're going to explain this further now. A solid of revolution is a solid whose shape we can create by revolving a 2D plane about an axis. Here on the left-hand side of the screen, we have a plot of the function y is equal to f of x is equal to root x. And that function is being plotted here from, well, on the closed interval from 0 to 2. Now the area, highlighted in green, is the region between the function curve f of x is equal to root x and the x-axis. This region is a 2D plane, so a two-dimensional plane. If we rotate or revolve this region around the x-axis, the region traces out a 3D shape, so a three-dimensional shape. Now this is a solid of revolution. We've created this 3D shape, shown here on the left-hand side of the screen, by rotating the region between the function curve f of x is equal to root x and the x-axis. We've rotated that two-dimensional plane around the x-axis, creating a solid of revolution. Now we can calculate the volume of this shape using the method of slicing that we described earlier. We find a formula for the cross-section area a of x, and then we integrate a of x over the extent of the shape along the x-axis. The only difference here is that our cross-sections are circles, or disks, whose radius is given by our function f of x. The cross-section area a of x at a point on the x-axis is the area of a circle. The circle's radius, r of x, is given by our function y equals f of x. In this example, r of x is equal to f of x, which is equal to root x. Now we can calculate the area of a circle as being equal to pi times the radius of the circle squared. In this example, our radius, r of x, that's equal to square root of x. Now we can calculate the area of the cross-section a of x as a of x is equal to pi times r of x squared. Now we can use our method of slicing equation to calculate the volume V as being equal to the integral from a to b of a of x dx. Now if we substitute in our a of x equation, we get that the volume V is equal to the integral from a to b of pi times r of x squared dx. So we can summarize this theory into a four-step method. In order to calculate the volume by rotation, or the volume of a solid of revolution, for a first step, we draw a diagram and choose the radius function r of x. So shown here on the right-hand side of the screen, we have the plot of a function y equals f of x is equal to root x. And that function is plotted here on the closed interval from 0 to 2. If we rotate the region between the function curve and the x-axis around the x-axis, we get a solid of revolution, a three-dimensional shape. For a second step, we square r of x and multiply by pi to get our area function a of x, giving us the area of our perpendicular cross-section as a function of x. So a of x, that's going to be equal to pi times r of x squared. For our third step, we find the limits of integration. This will be determined by the extent of our volume along the x-axis. So our lower limit of integration, that'll be equal to the furthest extent of our volume in the negative x direction, and our upper limit of integration, that'll be equal to the furthest extent of our volume in the positive x direction. Then for our fourth step, we integrate the function a of x over those limits of integration to find the volume. We can do that using our method of slicing equation, where the volume v is equal to the integral from a to b of a of x dx. If we substitute in our equation for a of x, we get that the volume v is equal to the integral from a to b of pi r of x squared dx. So we're now going to demonstrate that method for calculating the volume of a solid of revolution with an example problem and solution. So here we're going to calculate volume by rotation. We want to find the volume of the solid generated by revolving the curve f of x is equal to root x around the x-axis, where f of x is a continuous function on the closed interval from 0 to 2. So for our first step, we want to draw a diagram and choose the radius function r of x. Now here we're working with the continuous function y is equal to f of x is equal to root x, plotted on the closed interval from 0 to 2. So this is going to be our radius function. R of x is going to be equal to f of x, which is root x. Now if we rotate the two-dimensional region between the function curve and the x-axis, we're going to get a solid of revolution, this 3D shape shown here on the left-hand side of the screen. Our next step, we square r of x and multiply by pi to get our area function a of x. We have that r of x, that's equal to the square root of x. Now a of x, that's going to be equal to pi times r of x squared. Because r of x is equal to root x, a of x is equal to pi times the square root of x squared. So when we square the square root of x, we get that a of x is equal to pi times x. Now for our next step, we want to find the limits of integration. And this will be determined by the extent of our volume along the x-axis. The volume of the solid, it extends from x is equal to 0 to x is equal to 2. So our furthest extent in the negative direction is x is equal to 0, and the furthest extent of our volume in the positive x direction is x is equal to 2. So our lower limit of integration a, that's equal to 0, and our upper limit of integration b, that's equal to 2. And now for our next step, we want to integrate our area function a of x over our limits of integration to find the volume. So we can calculate our volume using our equation. The volume V is equal to the integral from A to B of A of x dx. Now we worked out earlier that A of x, that's equal to pi x. And we worked out earlier our limits of integration. A is equal to 0 and B is equal to 2. So when we substitute these values into our equation for the volume V, we get that the volume V is equal to the integral from 0 to 2 of pi x dx. Now we'll evaluate this integral on the next screen. So we have that our volume V is equal to the integral from 0 to 2 of pi x dx. Now pi, that's a constant, so using our constant multiple rule, we can take pi outside of that integral. So we get that our volume V is equal to pi times the integral from 0 to 2 of x dx. So keeping pi separate, we get that the volume V is equal to pi times x squared over 2 evaluated from 0 to 2. Now still keeping pi separate, that x squared over 2 evaluated from 0 to 2, that works out to be 2 squared over 2 minus 0 squared over 2. Now 0 squared over 2, that's just equal to 0. So we've got that our volume V is equal to pi times 2 squared over 2. So our volume V is equal to pi times 4 over 2. So our volume V is equal to 2 pi, and we're working with volume, so our volume is 2 pi units cubed. And that's our example, problem, and solution of calculating volume by rotation, also known as calculating the volume of a solid of revolution, and also known as the disk method.